All right, let's get started. So this video is going over vectors, at least starting vectors. I mean, we can do a lot with vectors, and that's both yay and oh no. It's kind of both, depending on your perspective. Vectors. Let's get I guess a definition, right? You're probably saying I'm watching this video for vectors. You better tell me what they are. So let's do that, right? So when I say vectors, okay, you might be thinking of Despicable Me, and that actually helps because what he says about magnitude and direction, that's true. That's what a vector is. And you're probably saying, well, I don't know what that means. A vector is simply, ready for this, a number with direction. Okay? To me, this is a really good way of thinking about it. All right? What does it mean? It means if I'm traveling, okay, I live in Iowa, if I want to go to New York, okay, back to my law school, if I want to go back to New York, I have to go east, right? And if I get in the car and start driving, and I go 85 miles an hour, I'm in a hurry to get there, okay? I get in an airplane and go 500 miles an hour. Okay, I better be going east, because if I go west, I'm not helping my problem. Now, somebody might be saying, well, eventually it'll come around. Yeah. That's because we live on a globe, right? But you get the idea, right? That I better have the right direction. Because velocity, speed is the word we often use, but velocity is a little bit different, right? Is a vector. It has direction. If I say I'm going 65 miles an hour, we just assume you're going in the right direction, right? But in physics, you better tell me which direction you're going. If it's a ball going 16 meters per second, where? Which direction? Up, down, left, right? 65 degrees off the horizontal? 35 degrees off the vertical? What do we mean? Okay, you have to be clear. That's because it's a vector. It's a number with direction. When we say number with direction, there's two components to that. There is what's called, is my keyboard going to behave? There is what's called magnitude. Magnitude. I think that's how you spell it. I don't know. I can't spell to save my life. Magnitude is just simply the size of the number, right? The size of the number. So, like, bigger number. As in bigger, I mean like 1,000, million, billion. That's magnitude, okay? And it could be negative. It could be negative 6 billion. The magnitude would be 6 billion, okay? You can think of magnitude as like the absolute value of the number, okay? So it's like if I had 16 meters per second, the implication, if it's positive, is that I'm going to the right in a problem or up, okay? If I said negative 16, the magnitude is still 16, right? The absolute value of negative 16 is 16. But now I've put a negative, and that negative tells me the direction, okay? And the direction is pretty much without exception. This would be whether it's negative or positive, okay? For those mathematically inclined students, you might be saying, is that why a number line is, to the right is positive? Yeah, exactly, right? Like this notion that we can use negative numbers to arbitrarily say this point is 0, and if you go up of it, it's positive. You go down of it, it's negative. If I go to the right of it, it's positive. If I go to the left, it's negative. Okay? It might help just to show, right, a Cartesian plane, right? If I'm in the first quadrant, the second quadrant, the third quadrant, or the fourth, right? If you think about it, right, if I'm up here, right, if I'm going up, that's positive. If I'm going down, it's negative, okay? If I'm going to the right, well, that's positive, right? So the first quadrant, right? If I'm a vector that is in the first quadrant, quote unquote, going in that direction, it's positive on both accounts. If I'm in the second quadrant, right, the implication is now I might be going to the left, which would make that negative, but I could still be going up, right? Just make these clear here, okay? The third quadrant's the real negative one, right, because we go down and we go to the left, and both would be negative. And then finally, the fourth quadrant, we could have, again, kind of split, right? You'll notice, again, mathematics is something that, when I took it in high school, I hated it. I was like, oh, boring memorization, I can't stand this. But if you try to make math interesting, if you try to find patterns, and kind of more what we're really trying to get at, which is how to be a problem solver, how to see patterns in numbers, patterns in graphs, you might be saying, wow, there's some symmetry across the origin, right? Yeah, that's pretty nifty, right? Mirroring, right, is the better word, I should say, right? Like mirrored across, okay? And that's not an accident. That's like, hopefully you're saying, oh, I kind of see what you mean there, okay? So what does it mean for right now? It means vectors are things that have a size, like how big the number is, yay, but then also we better respect the direction. So hopefully you're saying, I got it, cool, it's a vector, yay. This has huge implications for, let's say, if I have a free body diagram. So let's draw one real quick, right? If I were to push this, right, a force, I'm just going to say a force. I'm not going to put a person or a car. I'm just going to say a force. Call it the wind if you want. I don't really care. One force is pushing to the left. We usually just draw it as pulling. It doesn't make a difference as long as the arrow is going in the right direction. Let's say it's, I don't know, 2,000 newtons. Okay, it's to the left. Okay, here comes one of my dogs. Come to say hi, apparently. It's to the left, okay? Here I can leave it as positive 2,000, okay? And then maybe I have a force on the right. Maybe it could be friction. It could be a lot of things. Doesn't make a difference. Some force pushing the other direction with, let's say, 1,800 newtons, okay? Notice they're both positive, all right? If I were to make this negative, the implication is that now it's going this way, okay? So just be careful. Okay, if you do a free body diagram, you should always keep them positive, in my opinion. All right, just because if you do a negative, technically you're saying it's the opposite direction. Okay, so be careful. All right, so you say, okay, yeah, vectors, cool. Why do I need to care? Because now if I calculate the net vector, what's called the resultant vector, there's many names for this, I better make sure I calculate it properly. So if I say, hey, what's the net force in the x direction, F net x? Okay, that's my notation I'm going to use. Well, I have to take the sum of the forces, in this case in the x direction, right? That's what this is, so I take the sum of these forces. If you don't respect the fact that this is the opposite direction and make one of them negative, you're going to have a bad day. Okay, I'm going to tell you right now, there's no reason to make this negative. There's no reason to make that number negative, right? Because it's to the right. You might say, I don't like that. I'm left-handed. I don't like that. Well, it's convention. Convention means an agreement. Okay, if you really want to do your calculations that way, I guess you can. No one's going to stop you. But it's very easy to make mistakes, and people are going to be kind of confused if they're like, why are you making the right negative? But, hey, more power to you. It's a free country, I suppose. Okay, so calculating this, I'm going to say the sum of the forces in the x, well, that's equal to what? Negative 2,000 newtons plus, remember this is a sum, which means you're adding, so plus 1,800 newtons. And hopefully you can do this without needing a calculator, but if you need one, go right ahead. Our net force, right, our net force in the x direction, F net x, is equal to negative 200 newtons, which, suffice it to say, means this box, I haven't even given a mass, right? This is just for forces, is going to be accelerating that way, right? And you would say, oh, 200 newtons to the left, and then if we knew the mass of the box, we could figure out how much acceleration, for example, okay? This is all fine and good. Hopefully you're saying it's not that bad, all right? It gets messier when you factor in what are called components of a vector. So let me quickly show that, okay? So when we talk about vectors, we talked about magnitude, direction, yay. Vectors represent, right, velocity, let's say. I am going 65 miles an hour east. I'm going 65 miles per hour up. That's one dimension, right? One plane, or not plane, one direction as in one dimension. So whether I'm going up or down, that's the y. That's one dimension. If I'm going left or right, that's the x direction. That's the x dimension, okay? Generally speaking, we don't move in, like, go this way, turn, go this way, turn, go this way. We a lot of times make diagonals, right? So we need to take into account that there's an x component and there's a y component. And if you were taking college level, then you need to factor in x, y, and then a z, right, in and out. We don't do that in high school, though. Okay, maybe some high schools do. That'd be kind of cool. But I have not seen that. I'm sure it exists somewhere. How do we do this? We need to find what are called the components of a vector. So I'll put this right here, the components of a vector. All right. So when you do components of a vector, at this level, we're worrying about 2, the x and the y. Okay? So, simple vector. Let's say I have a vector that is, and we draw vectors as arrows, FYI. That's, you've probably seen me drawing them as arrows for a reason. This problem would be like, let's say we have, imagine like you're throwing a football. And let's say you're throwing it off of the x-axis, let's say 30 degrees. Okay? Notice I'm saying off the x-axis. If I just say 30 degrees, you should be saying 30 degrees off what? Okay? Because there's a huge difference between 30 degrees off the x and 30 degrees off the y. I hope you'd agree with that. Okay? And it's worth noting that it could be even worse, because if I say off the y, the assumption is the positive y. But I could say off the negative y, right? In which case, this would be an additional 180 degrees. Okay? Yes, there is math and physics. Okay? Anyway, 30 degrees off the x-axis, the positive x-axis in this case. Let's say the magnitude of this vector is, let's just make it easy, 100 newtons. Okay? What we're trying to find out right now is how much of that vector is up, like how much of me throwing the football is me going straight up in the air, right? And how much would therefore be to the ground, right? Like if I just threw it parallel to the ground, right? So we're basically splitting it into 2 pieces. And yes, it's not an accident that this looks like a triangle. Okay, triangles are not your best friend. In physics, triangles are your savior and your worst nightmare, I suppose. If you don't do them right, they're your worst nightmare. If you use them correctly, they're your savior, I suppose. Okay, drawing triangles, I know this thing sounds really stupid. If you're in an engineering class, you're in a physics class, when in doubt, draw triangles that there should be a t-shirt that says that. Okay, because they will help you. So I have the hypotenuse, right? The hypotenuse of this is 100 newtons. I have, in this case, 30 degrees. That's this angle here. If you want to call it angle theta, you want to call it angle phi, you want to call it angle sigma, you want to call it angle delta. Hey, it's up to you, right? But usually theta, right? Theta and phi, usually. Okay, but you go angle A, angle B, whatever. I don't care. It's up to you. But, just showing you what usually to say. So theta in this case is 30 degrees. How do we solve this? Trigonometry. Okay? And depending on which axis you're drawing off of, in this case we're drawing off the positive x-axis, right? That's where the angle is drawn from, relative to. That works nicely, because sine will give you the y component. Okay? And then cosine will give you the, oops, that's a horrible x, will give you the x component of the vector. Okay? So what does this look like? We would say that the sine of 30, right, the sine of 30 degrees, could you use radians? You could. It's worth noting in your calculator, you got to make sure you're in the right setting. Okay, in this case, degrees, and we use degrees in physics, it's fine. Okay? There was my dog going on the couch. My daughter left out all her craft stuff over there. So anyway, but yeah, sine in this case 30 degrees, and we're going to multiply this by the hypotenuse. This will give us the opposite side. Okay, and if you're like, how do you know that? Well, I'm a teacher. And you say, well, how can you prove that? Well, I'll show you. Right, sine is the opposite over the hypotenuse. Right, cosine is the adjacent over the hypotenuse. And then tangent is, there's 2 ways you could think of it, but let's do the way that, being consistent with this, is the opposite divided by the adjacent. Okay, and as a refresher, these are for right triangles. Okay, hypotenuse is always the longest side. It is opposite the right angle. That's the hypotenuse. It has to be the longest side. It's opposite the biggest angle. Okay, this is a right triangle. There cannot be an angle that is 90 or higher in a right triangle. There can't be 2, I should say, right? If it's a scalene triangle, right, then you could. But in this case, no. It's got to be, this is the biggest angle, therefore this is the biggest side. Okay? The opposite side would be, if this is my angle here, opposite side would be opposite. In this case, this guy, right? This would be the opposite side, assuming this is my angle. If I pick this angle, then it flips, right? So be aware. And then, of course, this side, think of it as it's touching, it's next to it, so we would call that the adjacent side. Okay, so the opposite, the adjacent, and the hypotenuse. Again, if I flip my angle, if I said, here's my angle, well, then they would flip, right? Then this would become adjacent, and this would become opposite. The hypotenuse is always the hypotenuse. That can't change, okay? But we're using this angle, okay? So if we use sine of this angle, we're going to find the length of this, okay? So sine of 30 times the hypotenuse, so times 100 newtons, is going to give us y, in this case, how tall the vector is basically the height of the vector. It's how much of this is going up. The force, how much of the ball is going in this direction. That's what we're basically trying to figure out here. Okay? So use a calculator. Oh boy, we're going to have fun with this calculator. Let's see if it's right. It's in degrees. Good. So we'd say 30, and then I think I have to say sine. Yep, there we go. Sine of 30 happens to be 0.5. There's a reason we use sine of 30 a lot. It's a nice number. Times, in this case, 100. And look at that, 50 newtons. 50 newtons, okay? And this is equal to, you could call this Fy, right? The vector F, in this case, I should call it that, right? That would be consistent. Okay, if I called it like vector A, then I would do AY, but in this case it's F, okay? So the component, the y component of vector f is equivalent to the sine of 30 times the hypotenuse, which in this case is 50 newtons. Okay, and then we can do cosine to find the x component of this. So cosine of 30 times the hypotenuse. This will give us the adjacent side, the x component. So let's see, we say, what, 30? 30, and cosine, do this kind of backwards, okay, times 100, and we're going to get like 86 point something, I believe. Yeah, 86.6. Okay, sig figs wise, I wasn't very consistent up here. I said 100. Technically, it's 1 sig fig. I'm going to put a dot here just so we're not worrying about sig figs being annoying. So 3 sig figs. So let's go. And by the way, 30 degrees, yeah, let's make that 30.0. Okay, just so we're not having to worry about that. I should be consistent with what I teach, yes. So 86.6. Okay, and you might be saying, well, how come it isn't 50? Well, because cosine of 30 is not 0.5. Okay, and this is 30 degrees. I want you to think about this. If I throw a football and I throw it straight in the air, the angle is 90, right? If I were to take the football and go throw it perpendicular to the ground, that would be an angle of 90. Sine of 90 is 1. Cosine of 90 is 0. None of the ball's momentum, none of its inertia is going to be going that way. It's going straight up in the air. Okay? If I threw it at a 180 angle, or a 0 angle is probably a better way to describe this, that means that there's no upward, right? There's no angle where my arm is moving up. It's just literally going like this. There's no y velocity. The velocity is just in the x. There's no momentum in the y. Does that make sense? Okay. As it happens, this was 30 degrees. So imagine I'm throwing the ball, and if you took a, what do you call it, a protractor and measured the angle of me throwing the ball, 30 degrees means most of its force is relative to the ground, right? Is in the x direction. So that makes sense. This is a bigger number than this. That makes sense. Okay? And then I could use this information, this is where we're going with this, to figure out, for example, how high does the ball get before it starts to go back down. I could figure out how far does it go before it hits the ground. Okay? I can't do that with this number by itself. I need to break it down into its components. Okay? Or be very clever algebraically, but it's still breaking it down. Okay? So hopefully this makes sense. Hopefully you're saying I get it. I know it's a long video, or longish, but hopefully it's making sense and making it easy for you. Okay? So that's vectors. Yay.